Hello, Accelerated Chemistry students. This is Ms. Crisipoli, and this is your Chapter 19, Section 2 video notes all over hydrogen ions and acidity. So water molecules are highly polar and are in constant motion even at room temperature. So on occasion, the collisions between water molecules are energetic for a reaction to occur. So if we have two water molecules that bang into each other, one of them is going to gain a hydrogen ion and become the hydronium ion, and the other one is going to lose a hydrogen ion and become the hydroxide ion. So this reaction is in which water molecules produce ions is called the self-ionization of water. So H2O as a liquid will become H plus and OH minus. In aqueous solutions, hydrogen ions are always joined to water molecules as hydronium. And remember, hydronium is H3O plus. So in pure water at 25 degrees Celsius, the concentration of the hydrogen ions is only 1.1 times 10 to the minus 7th molar. And the concentration of the hydroxide ion is also 1 times 10 to the minus 7th molar because the number of H pluses and OH minus ions are equal in pure water. Any solution in which your H plus and your OH minus are equal, we consider that a neutral solution. So the ionization of water is a reversible reaction, so Chatelier's principles apply. So adding either hydrogen ions or hydroxide ions to an aqueous solution is a stress on that system. So in a response, the equilibrium will shift towards the formation of water. The concentration of the other ions then will decrease. The ionization of water is a reversible process. Like we said, so Le Chatelier's principle will apply. So in aqueous solutions, like when H plus increases, OH minus decreases. Likewise, when H plus decreases, OH minus increases. For aqueous solutions, the products of the hydrogen ion concentration and the hydroxide concentration equals 1.0 times 10 to the minus 14th. So if we were to look at that, we would multiply the concentration of H plus times the concentration of OH minus, and we'd get 1.0 times 10 to the minus 14th. The product of the concentrations of the hydrogen ion and the hydroxide ions is called the ion product constant for water. And that value is 1.0 times 10 to the minus 14th, and it is an important value that you should memorize. So for acidic solutions, when some substances dissolve in water, they release hydrogen ions. Hydrochloric acid is one of those things. So the hydrogen ion concentration is going to be greater than the hydroxide ion concentration. And a solution in which your hydrogen ion concentration is greater than your OH minus ion concentration, you are going to have an acidic solution. And that means that your H plus is going to be greater than 1.0 times 10 to the minus 7th. So let's look at how we can use the ion product constant for water to solve for some values. So if the H plus concentration in a solution is 1.0 times 10 to the minus 5th molar, is the solution acidic, basic, or neutral? And what is the OH minus concentration of the solution? Let's set up our problem. We're going to use the expression for the ion product constant for water and the known concentration of the hydrogen ions to find the concentration of our hydroxide. So we know H plus is equal to 1.0 times 10 to the minus 5th. We know what Kw is. That's our constant, 1.0 times 10 to the minus 14th. And we don't know if it's acidic, basic, or neutral, or what our OH minus concentration is. So let's set this up. We're going to use the H plus to determine whether the solution is acidic, basic, or neutral. So 1.0 times 10 to the minus 5th is greater than 1.0 times 10 to the minus 7th. So this solution is acidic. Now we need to calculate what our OH minus ion concentration is. So we're going to use our equation Kw equals concentration of H plus times the concentration of OH minus. We're going to rearrange that and solve for OH minus. And then what we're going to do is we're going to plug in our values. So we're going to plug in what Kw is, which is 1.0 times 10 to the minus 14th, all over what our H plus ion concentration is, which is 1.0 times 10 to the minus 5th. And we're going to solve. So we're going to get 1.0 times 10 to the minus 5th is our concentration for our OH minus. And if H plus is greater than 1.0 times 10 to the minus 7th, then OH minus must be less than 1.0 times 10 to the minus 7th. And 1.9 is less than 1.0 times 10 to the minus 7th. So our solution is correct. Expressing hydrogen ion concentrations in molarity is not practical. A more widely used system for expressing H plus ion concentrations is the pH scale. The pH scale runs from 0 to 14. And if we're looking at our pH, the pH of a solution is a negative logarithm of the hydrogen ion concentration. So pH is equal to negative log of our H plus. So in pure water, a neutral solution, the H plus is 1.0 times 10 to the minus 7th, so the pH is 7. So if we take the negative log of 1.0 times 10 to the minus 7th, the log of 1 is 0, and the log of 10 to the minus 7th is minus 7, and we're putting negative out front, so that's going to equal a positive 7. If the H plus of a solution is greater than 1.0 times 10 to the minus 7th, the pH is less than 7. If the H plus concentration is less than 1.0 times 10 to the minus 2nd, then the pH is going to be greater than 7. So a solution with a pH less than 7 is acidic, a solution with a pH of 7 is neutral, and a solution with a pH greater than 7 is basic. So if we were to look at this relationship of H plus ions and OH minus ion concentrations, for normal things that you see how once you have a low pH, you're going to have something that's acidic, and it's going to, as your pH gradually increases and becomes higher, you're going to have a more basic pH. So we can calculate pH from H plus concentration. So if we express the H plus in scientific notation, you can make it easier to calculate your pH. So if you were to write 0.0010 as 1.0 times 10 to the minus 3rd, we would know that the pH for that solution is going to be 3. Now this only works if your coefficient is 1. The two numbers to the right of the decimal point represent the two significant figures of the concentration. So it is easy to find pH for solutions when the coefficient is 1. The pH of the solution is going to equal the exponent with the sign change from minus to plus. So if you have a solution that has an H plus concentration of 1 times 10 to the minus 2nd, it's going to have a pH of 2. When the coefficient is a number other than 1, you're going to need to use a calculator with a log function key to calculate your pH. So let's calculate pH from the H plus concentration. So what is the pH of a solution with a hydrogen ion concentration of 4.2 times 10 to the minus 10th? We're going to use the pH, we're going to use our concentrations to find the pH using the pH equals negative log of our H plus ion concentration. Let's list out our knowns and what we're trying to find, as always. And we're going to start with the equation for finding pH from H plus. So pH equals negative log of H plus. So what we're going to do is we are going to substitute our concentration of H plus in, and we're going to solve for our pH. So our pH equals negative log of 4.2 times 10 to the minus 10th, which is going to be negative of a negative 9.37675, which will be 9.37675. And we're going to round it to 2 sig figs, or 2 decimal places, 3 significant figures. And that is because our concentration is to 2 sig figs, 4.2, 2 sig figs. And for pH, when you're asked about how many decimal places do you need to round to, it's always going to be based on the sig figs in your concentration. So now we have to make sure this makes sense. So the value of the hydrogen ion concentration is between 1.0 times 10 to the minus 9th and 1 times 10 to the minus 10th. So the pH should be between 9 and 10, and it is. Now let's calculate H plus from pH. You can calculate the hydrogen ion concentration if you know the pH. The pH is an integer, and it's easy to find the H plus concentration. So if you have a pH of 9, that means your concentration is going to be 1 times 10 to the minus 9th. Most pHs, though, are not whole numbers. So when the pH value is not a whole number, you're going to need a calculator with an anti-log, or that 10 to the x button, so you can accurately get your hydrogen ion concentration. Let's try that. Let's calculate the H plus from pH. So the pH is going to be 6.35, And what is the H plus ion concentration? So if we're going to do this, we're going to use the anti-log, or that 10 to the x function on our calculator. We know our pH, we don't know our H plus. So this is how we're going to set this up. We're going to swap the sides, so pH equals negative log, so I'm going to do negative log of H plus equals pH. Negative log of H plus equals 6 times 6.35. And so what we're going to do is we're going to use that anti-log. So we're going to do negative, so 10 to the negative pH, which is going to be 10 to the negative 6.35. When we do that and we solve, we get our H plus concentration is 4.5 times 10 to the minus 7th. And remember, our pH had 2 decimal places in it, so our answer needs to be rounded to 2 sig figs. Let's calculate pH from OH minus concentration. So if you know the OH minus concentration, you can find its pH. You can determine the H plus ion concentration first, and then solve for your pH. So let's do that in a problem. So what is the pH of a solution that has an OH minus concentration of 4.0 times 10 to the minus 11th? So what we're going to do is we're going to find H plus by dividing Kw by OH minus. Then we're going to solve for our pH like we did in the sample 19.3. So we know our OH minus concentration, we know Kw, what we don't know is pH. So we're going to start with the ion product constant first to find H plus. So we're going to rearrange that equation. So H plus in this case is going to be our Kw divided by our OH minus concentration. Then we're going to plug in our values. So 1.0 times 10 to the minus 14th. Remember, that is Kw. That is a constant. That number is never going to change. And we're going to divide that by our OH minus concentration. And we're going to get 0.25 times 10 to the minus 3rd moles, or 2.5 times 10 to the minus 4th is the better way to write that. Then what we're going to do is we're going to find pH. So to substitute for pH, we're going to do negative log of our H plus that we just found. That's going to be negative log of 2.5 times 10 to the minus 4th. And we're going to solve for that and get a pH of 3.60. Remember, our concentration of our OH minus that we were given had 2 sig figs in it, so that means our pH needs to have 2 decimal places in it. And let's evaluate to make sure it makes sense, and it does. Now let's talk about how we can measure pH. You can either use an acid-base indicator or a pH meter to use pH. Acid-base indicators are different compounds that you stick in a mixture of an acid and a base, and they change color based on pH range. Or you can actually use a pH meter, which is an electronic device that has a probe you can stick into your solution, and it will read the pH via the conductivity that you're seeing in the solution. So an indicator is an acid or a base that dissociates in a known pH range. So indicators work because their acid form and their base form have different colors in solution. So the acid form of the indicator is going to be dominant at low pH and at high concentrations of H+, and the base form is going to be dominant at high pHs and high OH- concentrations. So the change from dominating acid form to dominating base form will allow for us to determine what the pH of the solution is, and that's going to happen within a narrow range of 2 pH units. So at all pH values below a range, you will see only one color of the acid form, and at all pH values above this, you will see the color of the base form. Many indicators are needed to span the entire pH spectrum. So some of these do overlap, as you can see what pH range they see. We will mostly be using phenolphthalein for our labs that we're going to be doing in the future, because we're going to be using things where we want basic pHs at the end. So you can also use indicator strips, and indicator strips are pieces of paper or plastic that have been soaked in an indicator and then dried. The paper is then going to be dipped into the unknown solution, and the color that results is compared with a color chart to measure the pH. Some indicator paper has absorbed multiple indicators, and the colors that result will cover a wide range of pH values. Or we're going to use pH meters. So you can use a pH meter is used to make a rapid continuous measurements of pH. The measurements of pH obtained with a pH meter are typically accurate to be within 0.01 of pH unit true to the pH value. If the pH meter is connected to a computer or chart recorder, the user will have a record of the pH changes. And a pH meter can be easier to use than liquid indicators or indicator strips because the pH reading is visible in a display window on the meter, and the color and cloudiness of solution do not affect the accuracy of the pH. And as always, all the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition textbooks resources CD and pearsonchem.com. Thank you so much. Have a good night.